Hello once again, class, and welcome to another mock lecture. Today we're going to be talking about fundamental trig identities. Let's get stuck into it by asking the most fundamental question that there is. What even is an identity? Well, very basically, an identity is an equality statement between two things. So like A is equal to B, right? That's an identity. Some expression A being equal to some different expression B. It's when you can represent the same entity or function or expression in a different type of form. In a different form in general. We actually already know a bunch of identities, right? We know the reciprocal identities. We know that sine of theta is 1 over cosecant theta, secant is 1 over cosine, so on and so forth. And we also know the quotient identities. Okay, and all of this basically stems from our diagram of the unit circle, except that in this particular picture, R is just 1. That was a complete accident, but I didn't want to rewrite every single slide, so you're just going to have to pretend that these intersections don't exist. Because we don't actually have to define sine and cosine and all the trig functions based on a unit circle. You can actually, you can define them on a circle with radius r. It's just that now sine, instead of just being the y coordinate of the intersection of the terminal side of the angle and the circumference of the circle, now it's y over r, right? Cosine is x over r. Okay, so that's an important distinction. You're going to have to kind of mentally block out all those intersections for basically the entire video. Now, you might be wondering, why do we need to know identities? Well, the first thing that I want to talk about is simplification, right? You can use identities to simplify certain expressions so that they're easier to use. Like, for example, tangent theta, cosecant theta, right? It's not a super complex expression, but you can simplify it to make it easier to work with. For example, the tangent of theta is sine over cosine, right? That's just by the definition of tangent, right? It's a quotient identity. Cosecant, using a reciprocal identity, could be rewritten as 1 over sine, right? So tangent, we're replacing that with the identity sine theta over cosine theta. Cosecant's being replaced with the reciprocal identity 1 over sine. And then I'm just going to multiply those things together. Now this over here is the justification for what it is that we're doing. This is why I was able to do this. So typically the way that I like to lay things out is I put all my arithmetic stuff over here, and then I put my reasoning on this side, right? It's kind of my justification for what we're doing. So I said this is equal to this by the quotient identity for tangent and the reciprocal identity for cosecant. I encourage you to do this too, but you don't necessarily have to be this thorough. You could do something like by quotient and reciprocal identities, okay? Now I'm just going to use some multiplication, right? Multiplying fractions, you just multiply them straight across. Notice you've got a sign in the numerator and a sign in the denominator, so those cancel. So you just get 1 over cosine. And my justification for this step is basically just algebra. I'm just simplifying stuff. 1 over cosine is secant by a reciprocal identity for secant theta. So therefore we can conclude, right? We started here, we ended here. There's equal signs all in between. So these things are equal. Really by transitivity, but you don't necessarily need to cite that as a justification. So I'm just going to say, therefore, the tangent theta, cosecant theta, the multiplication of those two functions can just reduce to and is secant theta. And this is technically an identity. We just proved our first identity. We just showed the tangent theta, cosecant theta is equal to the secant of theta. I'm not going to really add it to this list at all, but it is an identity that we could refer to at some point. Now, and again, remember to cross those things off in your mind. This is just a general circle, not particularly a unit circle. But what I want to do is add to this list, okay? Today we're going to talk about finding more identities, 9 more identities, in fact, which sounds like a lot, but it's really not. It comes in 2 categories, 2 flavors of identities today. The first one is examining this triangle, okay? So I'm just basically extrapolating this triangle and putting it over here, and we're going to do some Pythagorean theorem business with this stuff. X squared plus y squared is equal to r squared is the Pythagorean theorem. It's a right triangle, which is why we're allowed to do this. And for no inexplicable reason other than for funsies, I'm going to go ahead and divide everything by the radius, the square of the radius, just because I can, okay? On the right-hand side, r squared divided by r squared, that is 1. That just reduces to 1. X squared divided by r squared could be rewritten as x divided by r quantity squared, and we can do that because of an exponent property. And we were going to do the same thing with y over r. Now, if you look over here, sine is y over r, cosine is x over r. Those are equal to each other based on the definitions of this non-unit circle, of this circle that we have here. So I'm going to replace x over r with cosine, and I'm going to replace y over r with sine. And then I'm just going to rewrite this in a way that we're allowed to write squared of trig functions. These are equal, right? This is a better way to write cosine of theta quantity squared is cosine squared theta. Sine theta quantity squared could be rewritten as just sine squared theta. But here we go. That is a new identity, and that one is worth writing down, and that is actually our first of 3 Pythagorean identities. The other 2 Pythagorean identities actually just come from the original one. So rest assured that if you ever forget the other 2 Pythagorean identities, and honestly, I don't even remember what they are off the top of my head, and I just wrote these slides. But I know, and I'll always know, that the cosine squared of theta plus the sine squared of theta is equal to 1. This is true for any theta, by the way. Literally any angle, any real number you plug into there, cosine squared theta plus sine squared theta always going to be equal to 1. And I can generate the other 2 identities from this. First, we could just divide both sides. Oh, by the way, this slide is about just showing you if you are working on a unit circle. This is literally the Pythagorean theorem for this triangle, right? On a unit circle, this distance is cosine theta. This distance is sine theta. A squared plus b squared is equal to c squared. So you literally get cosine squared theta plus sine squared theta is equal to 1. So we could have actually just got this Pythagorean identity based on the unit circle, but I went ahead and just used any, again, these are not there. Pretend they're not there. They're not there. Any radius circle to generate it. But in any case, I could divide this entire thing by cosine squared theta. Okay, I'm going to divide the left-hand side by cosine squared theta, and since it's separated by addition, it means I've got to divide both pieces by the cosine squared theta. And then on the other side, we're going to divide by cosine squared theta, right? Well, 1 divided by cosine, right, is secant. That's a reciprocal identity, right? Now, technically, we do have secant squared because we've got 1 divided by cosine squared, but I could certainly just do, let's see, which identity is this? This, I could do that, and that. That's a squared. Right, and that identity still holds true. So, and same thing could be said for the tangent, right? Sine squared over cosine squared is sine over cosine quantity squared, which is tangent quantity squared, or tangent squared theta. And then here, cosine squared divided by cosine squared, that's just 1. That's another Pythagorean identity. 1 plus the tangent squared theta is equal to the secant squared of theta. You can also divide by sine squared theta from the original one to generate this one. Cotangent squared theta plus 1 is equal to cosecant squared theta. So these are very important. These ones, Pythagorean identities, super useful, even outside of this class. In calculus, you're going to use this identity all the time, all 3 of these. Now, and actually, I don't know if you remember this, but a couple videos ago when we talked about the other trig functions, I gave you guys this crazy looking diagram. It's the physical representations of the lengths of sine and cosine and tangent, and really all the other trig functions based on the unit circle. And the thing I want to point out is that the triangle secant theta, tangent theta, and 1 is inside of it's on the unit circle. It's on this picture, right? So if you're going to use Pythagorean theorem on this triangle, you would have 1 squared, which is 1, plus tangent squared is equal to secant squared. So and then here's the other one, right? Cotangent squared plus 1 squared, which of course is just 1, is equal to the cosecant squared of theta. So these Pythagorean identities actually just come from the triangles that you can draw inside or on the unit circle picture based on the physical length representation of all the trig functions. So I'm using the actual length definition of sine and cosine as opposed to the y coordinate, x coordinate, respectively, definition. But all these triangles do exist as right triangles on this picture, and that's why they go together. That's why sine and cosine go together, because they form a right triangle with a side length of 1. In that case, the hypotenuse is 1. Tangent and secant form their own triangle. That's this one, right? In this case, the adjacent side, right, is 1. Cotangent and cosecant form a triangle, right? In that case, the opposite side is 1. So that's another way that you can look at where these Pythagorean identities come from. Okay, so let's do some examples. Let's use these identities because that's why we're learning them, to use them. Let's write sine x and cotangent x in terms of cosine of x, given that cosecant of x is greater than 0. Now, when you first read this, you might be like, what the heck what are we even doing here? Well, here's the goal, okay? We need to write sine of x is equal to, and then after the equal sign, the only trig function that should show up is a cosine of x. That's what writing a function in terms of another function is all about. Right? If I said, let's write y in terms of x, you'd have y is equal to, and then a bunch of stuff that only involves x in it. We also need to show that cotangent of x is equal to some bunch of stuff, right, with cosine as the only trig function that's involved. So the first thing I think about is, well, how can we even relate sine and cosine to begin with? Well, first thing we could do is we could set up the identity, right? So we're going to start with sine squared of x is equal to 1 minus cosine squared x. Now, by the way, you might be thinking, how the heck did you get this, Mock? Well, check it out, right? The Pythagorean identity says sine squared of x plus cosine squared of x is equal to 1. So I'm just going to subtract cosine squared x from both sides. They cancel on the left, and check it out, we're done. Right? That's how you get sine squared of x is equal to 1 minus cosine squared x. So the lesson here, right, is just because it's written as sine squared x plus cosine squared x, or cosine squared x plus sine squared x is equal to 1, doesn't necessarily mean you have to use that specific form of the identity. It's an equation, right? Whatever you do to one side, as long as you do to the other, you're keeping your equation balanced. So this, right, this is equal to this is still that same Pythagorean identity. Okay, well anyway, I want to solve for sine of x. I don't want sine squared of x, so I'm going to square root both sides, and you're going to get plus or minus the square root of the right-hand side, which is 1 minus cosine squared x. However, we're given that this is true, right? Cosecant x is greater than 0. Which means that the sine of x is greater than 0, right? Because cosecant is sine's reciprocal, and reciprocals don't change the sign of the function at all. And I'm saying sine as in S-I-G-N, right? The positive or negativeness. Since cosecant x is positive, we can conclude that sine is positive as well. Sine of x is positive, okay? Which means we can do away with the plus or minus. It's plus. Right, sine is positive, so it's the square root, the positive square root, the principal square root of 1 minus cosine squared of x. Okay, so that takes care of sine. Cotangent. How can we get cotangent in terms of cosine only? Well, we do know that cotangent of x by a reciprocal identity is cosine of x divided by the sine of x, and we conveniently just solved for sine of x in terms of cosine of x. So I'm just going to replace sine of x with this thing that we just found, and here we go. Cotangent of x is equal to only stuff that involves cosine. Mission accomplished. Okay, here's another one. Let's say we want to simplify this expression. So we've got secant squared theta minus 1 times the cotangent squared of theta plus tangent squared of theta. This is kind of a nightmare of stuff if you're going to like solve, like maybe you want to do something like this. Right, as it's written, that's kind of annoying. That's extremely annoying, in fact. Like, where do we even start? So maybe we should simplify the left-hand side of this thing first. So the first thing I'm going to do is realize that secant squared theta minus 1 is the tangent squared of theta. That is by a Pythagorean identity. The Pythagorean identity specifically is this, and I'm just subtracting 1 from both sides, and I'm realizing that secant squared theta, I don't know why there's 2 squared there, secant squared theta minus 1 is equal to tangent, right? That's this side is this. So this thing can just be replaced by the tangent squared of theta. And then we've also got all this other stuff still. Haven't really done anything with the cotangent squared theta or the plus tangent squared theta. But my justification for turning this into this is the Pythagorean identity. Next, I factored out a tangent squared theta. Right, we have 2 things here, and I was like, look at this. They both have a tangent squared theta in common, so I'm going to factor that thing out. So I'm just going to do a little bit of algebra. 1 plus cotangent squared theta is cosecant squared theta. Like, just straight up. That's a Pythagorean identity. So then what I did is I realized, well, look, it's some squared trig function times another squared trig function. I can rewrite that as, well, I don't know why I'm rewriting it. It's right here. As the tangent theta cosecant theta squared. That's by an exponent property that says when you square products, you apply the power to both pieces of the product. So squaring this thing would just get me back to here. So I know these two things are equal. Tangent theta cosecant theta is secant theta. And we proved that. That was like one of the first things we did in this video. Tangent theta cosecant theta is secant theta. So this whole thing is just secant theta from identity at beginning of video, and then secant theta quantity squared is just equal to secant squared theta. So this whole mess of stuff is just the secant squared of theta, right? And that's significantly easier to solve if you're setting it equal to 0. Although secant is never 0. It's outside the range. Let's ignore that for now. Now, by the way, you might be looking at this and you might be thinking, well, hold on, Mock, like that's cool, but my first instinct was to distribute the cotangent squared, right, to the secant squared theta and to the -1. I invite you to pause the video and do that, and you're going to find that you get the same thing, which is actually really cool. There's multiple different ways to go about doing these identity simplifications, or in some cases, identity verifications. And so you're allowed to be as creative as you want with this stuff. And just because you don't end up simplifying the way that I've shown you doesn't mean you're doing it incorrectly. There's a whole bunch of different ways to do this. And in fact, I encourage you to look for different ways, because my way is certainly not always going to be the best way. Case in point, this problem. I don't even know if this is the fastest or most elegant way to simplify this thing. This is just what I saw, so it's what I did. Here's another cool thing we can do with identities. Let's say we want to expand this thing. Right, so actually multiply this thing out. Now, before we do that, I'm just going to recap real quick algebraically what happens when you square a binomial. So a plus b squared. It is certainly not a squared plus b squared. Okay, it's not a squared plus b squared. Listen, a plus b quantity squared is not equal to a squared plus b squared. Instead, it's a plus b times a plus b, right? That's what happens when you square something. Now to do this, you can use the FOIL method, which is my non-favorite way to expand a binomial. Or you can use the box method, which is just setting up, in this case, a 2x2 square. Box maybe means 3-dimensional, but I still call it the box method because that's what I like. But you're just constructing a 2-dimensional array, basically. A multiplication table, if you will. I am talking about this way too much. You get this, right? Whether you're going to FOIL or use the box method or whatever you're going to do. Okay, so same thing applies over here. Okay, cosine x plus sine of x quantity squared is cosine x plus sine x times cosine x plus sine x. So we're just going to use the box method just like the other time. And we get this. Cosine squared x plus 2 cosine x sine x plus sine squared of x. But we're not done. And that is honestly one of my favorite things about trig identities. We're done here. There's nothing else we can do to simplify this. However, here, there is still something we can do to simplify this. There's a cosine squared x and a sine squared x inside of this expression. Since addition is commutative, let's just move stuff around and put them together. Cosine squared x plus sine squared x is 1. So we get 1 plus 2 cosine x sine x, and that's by a Pythagorean identity. Last one, before we get into some other stuff. Let's say that we want to, and this is actually a really useful tool. Sometimes when you have an addition, you'd be better off if you could somehow write that as a multiplication. So let's say you have the tangent of x plus the cotangent of x, and we want to write this instead of a sum of two trig functions, which is what it currently is. Let's say we want to write it as a product of two trig functions. Okay, well, the first thing that I'm going to do, and oftentimes this is just my general approach to solving identity, to proving identities, verifying identities, simplifying expressions, get everything in terms of sine and cosine. Sine and cosine are super versatile and part of a ton of different identities. So typically, if you can get something in terms of just sine and cosine, you can do a lot of stuff to it. Here, I've just used the quotient identity on both tangent and cotangent. And I'm going to just find common denominators. I'm going to actually add these two things together. So that means I need to multiply sine of x over sine of x on the left-hand side to match this denominator, right? And on the right-hand side, I need to multiply by the missing factor in the other denominator, which is cosine of x. So we get this, right? The common denominator is sine x cosine x. Going back one slide, sine of x times sine of x gives you sine squared x in the numerator for this first fraction. The other one gives you cosine squared x. So I'm just going to put that over here as my next step, and then I'm actually going to add them together, right? And when you add fractions with already common denominators, you just leave the denominator what it is, but you add the numerators. The numerator, you might see, is 1. It's sine squared x plus cosine squared x. That's 1 by a Pythagorean identity. And now we don't have an addition anymore. So things are looking pretty good. 1 over sine x cosine x could be rewritten as 1 over sine x times 1 over cosine x, which by some reciprocal identities is just cosecant x, secant x. And so that's the same as tangent of x plus cotangent of x. If you graph this on Desmos and then graph this on Desmos, they're going to overlap and be the exact same function. Now again, you might wonder, how is this useful? What is the point of doing this? Writing a sum as a product, who cares? Well, what if it's equal to 0? Right? What if we're going to solve tangent of x plus cotangent of x is equal to 0? Okay, that's really hard to do when you have two different functions that are occurring in this case with no multiplication, right? They're just being added. But now that we know it's cosecant x, cosecant x, okay, let's just get rid of that, times secant x is equal to 0, you can just use the zero product property at this point. If you have two things that are multiplied together to give you 0, then you break them apart. It's either the case that cosecant x is equal to 0 or the secant of x is equal to 0. Okay, that's so much easier to solve. Now, of course, you might be wondering, Mock, why do you keep using secant and cosecant equal to 0? They're never equal to 0, right? Their graphs do this sort of maneuver, right? Zero's here. It's this line here. They literally never intersect the x-axis. Yeah, this probably isn't the best example. But the point remains. You could do something. You could at least say, oh, look, there is no solution to this thing because these don't have any solutions. Cosecant and secant never intersect the x-axis. Anyway, moving on. Let's go back to here. So let's add to this thing. Now to do that, we're going to need to do a little bit of review. What we're going to review is odd and even functions from a pre-calculus class. So first things first, if f of x is reflectionally symmetrical across the y-axis, then f of x is an even function, and we have the mathematical definition, f of x is equal to f of negative x. So it's some graph that's reflectional about the y-axis. So think x squared, right? Y is equal to x squared is an even function because if you reflect it over the y-axis right here, it's going to line up with itself perfectly. If f of x is rotationally symmetrical about the origin, then f of x is an odd function, and negative f of x is equal to f of negative x. That's the mathematical definition. So think like x cubed, right? Something like this. Right? If you rotate that 180 degrees, it is going to look exactly the same, at least if I were to draw it with any semblance of symmetry, but x cubed is definitely symmetric. So let's get back to trigonometry. There's 4 functions that have rotational symmetry about the origin. Sine of x, tangent of x, cosecant x, and cotangent of x are all odd functions because if you flip them all 180 degrees, if you basically look at them upside down, their graphs are going to look exactly the same. Cosine and secant have reflectional symmetry across the y-axis. If you fold it in half across the y-axis, you're going to get the exact same function on both sides, so cosine and secant are even functions. So let's add this to our identities list. We're going to call these the negative angle identities. And it's the sine, cosine, cosecant, secant, tangent, cotangent of negative theta. What's it equal to? Well, here's all the odd functions, right? This just comes from the definition f of negative x is equal to negative f of x, right? That's the definition of an odd function. So the negative just comes outside of the parentheses, basically. That's true for odd functions. Even functions, cosine of negative theta is equal to the cosine of theta, secant of negative theta is equal to secant theta. So let's just do one more example, I promise, and we're going to be done. And we're just going to throw negative angle identities into the mix here. So we've got secant squared of negative theta divided by negative cosecant squared of negative theta. So first things first, I'm going to go ahead and rewrite these things so that I can actually use the negative angle identities. Because we actually don't have a negative angle identity for when we have a squared in the mix. So I just rewrote these using the definition of squaring a trig function. So I've got the quantity, secant of negative theta, that's squared. And we're going to divide that by negative. and then cosecant negative theta squared, because the negative is actually on the outside. It's actually separated, right, from the cosecant. It's being multiplied. That's a better way to think about it. So it's -1 times this thing, and that's why I put it in its own bracket here. Now I'm going to use the negative angles. So secant is an even function, so we have the secant of theta on the top instead of secant negative theta. Cosecant is an odd function, so its negative angle identity says that cosecant negative theta is basically just bringing out the negative. So we've got this. Then I square the top and the bottom. Now you might be wondering, okay, Maki squared, why is there still a negative? Listen, this negative got squared and became positive, but this negative is still hanging out in front. So that's where that came from. I'm going to think about this as division, like this. I mean, it is division, but instead of like writing it as like a big bar division, a fraction, there we go, I'm going to write it as secant squared theta dividing sign negative cosecant squared theta, because I'm going to use the reciprocal identities on these things. So secant squared theta, that's in terms of cosine, 1 over cosine squared theta. We're going to divide that by -1 over sine squared theta, because that's cosecant's reciprocal identity. All right, when you divide fractions, you flip and multiply the second one. So that's what I did here. This is just some algebra is what we're doing. So 1 over cosine squared theta times negative sine squared theta over 1. Multiplying them together is just multiplying them together. The top and the bottom each have a 1 in it. So we basically just put these together, and that's our fraction. And then, of course, sine divided by cosine is the tangent function. So we get negative tangent squared theta by the quotient identity. All right? And we are done. Okay? We can make this conclusion. So hopefully you guys learned something. Hopefully this wasn't too long of a video. If you guys have any questions, please leave them in the comments. Thanks a ton for watching, and I'll see you in the next one.